Hello students, today we are going to learn conductance of electrolytes. This is present in the electrochemistry unit of class 12 NCERT. We will look at the following topics. First, you will learn the difference between resistance and conductance. How to classify materials based on conductivity. What is the difference between metallic and ionic conduction? How to measure the conductivity of electrolyte solutions. The concept of molar conductivity. Finally, Kohlrausch law of independent migration of ions. First, let us look at the concept of conductance. Then we will go to the concept of resistance. Conductance is the ability of a material to allow electricity to pass through. If you take a plate of copper and connect it to a battery will supply electricity. The electricity will pass through the copper plate. How do you know whether electricity is passing through or not? You have to connect the copper plate to a conductivity meter or a galvanometer. Then it will show a deflection if current is passing through the material. Instead of a copper plate, if you connect a piece of glass, current will not pass through because glass is an insulator. Copper is a conductor. Next point is the conductance is directly proportional to the area of the material. If you increase the area of the copper plate, more current will pass through. That is, conductance will increase. At the same time, it is inversely proportional to the length. If you take a longer copper plate, then the conductance will be less. The symbol for conductance is G. To summarize this, we can write as G is proportional to A, area, by L, length. To get more clarity on this concept, I have prepared an animation for you. Now, let us look at the animation. Now you see that we have connected a copper plate to a battery. The negative terminal is here to the left and the positive terminal is here in the right side. Now, after connecting the battery, electrons will flow through the copper plate from the negative terminal to the positive terminal. You can see that electrons are flowing from negative to the positive side because copper is a conductor. When the electrons are flowing, they have to cross the vibrating copper atoms in the copper plate. You know that all materials are made of atoms and molecules. The atoms are not in constant position. They are always vibrating even at room temperature. So if you increase the length of the copper plate, the electrons should pass through more and more vibrating atoms. The vibrating atoms create a hindrance. They create the resistance for the flow of electrons. As we increase the length of the copper plate, the electrons will scatter because of more and more vibrating atoms. As a result, what happens? The conductance decreases when we increase the length. Now, we will see what happens if we increase the area of the copper plate. More and more electrons can pass through the copper plate. As a result, conductance increases. Now you clearly understood why conductance increases with area and decreases with length. Now let us go back to the PowerPoint. Having understood why G is directly proportional to A and inversely proportional to L, now we can remove the proportionality by adding a proportionality constant. We get the expression G is equal to kappa A by L. Kappa is the proportionality constant. It is called conductivity or specific conductance. The SI unit of conductance is Siemens or ohm inverse, whereas the SI unit of conductivity is Siemens per centimeter or ohm inverse centimeter inverse. What is the difference between conductance and conductivity? Conductance depends on the dimensions of the conductor. Just now we saw that G will increase if you increase the area of the material. It will decrease if you increase the length of the material. Whereas conductivity, kappa, is the proportionality constant. So it will not depend on the dimensions of the conductor. Whether you take 1 meter copper wire or 2 meter copper wire, the conductivity value will be the same because you see it is already normalized. The unit is Siemens per centimeter. So it is a per centimeter value. So the conductivity is a constant for a given material. Then the third point is both conductance and conductivity. Both of them depend on the nature of the conductor, temperature of measurement, and pressure of measurement. Therefore, you understood that conductance is not a constant, whereas conductivity is a constant for a given metallic conductor. The next concept is resistance. Resistance is the reciprocal of conductance. Resistance is equal to 1 by conductance. We can write it as an expression R is equal to 1 by G, which is equal to 1 by kappa L by A. 1 by kappa can be written as another constant rho. Here the proportionality constant rho is called the resistivity or specific resistance. We saw that kappa is conductivity. Here rho is resistivity or specific resistance. Whenever you say the word specific, it means that value is specific to the given material. You know, specific gravity, specific surface area. So whenever you see that word specific, you understand that it is a constant for a given material. The SI unit of resistance is ohm, whereas the SI unit of resistivity is ohm centimeter. What is the difference between resistance and resistivity? Just as in the case of conductance versus conductivity, we saw that here also resistance depends on the dimensions, whereas resistivity does not depend on the dimensions of the conductor. The unit of resistance is ohm, whereas the unit of resistivity is ohm centimeter. Both the parameters depend on the nature of the conductor, temperature, and pressure of measurement. Resistance is not a constant, whereas resistivity is a constant for a given metallic conductor. We can classify the materials based on the conductivity values. If you look at the diagram, you can clearly understand. If the conductivity value is greater than 10 power 3 Siemens per centimeter, it is called a conductor. Example, copper. If the conductivity value lies between 10 power minus 7 and 10 power 3 Siemens per centimeter. It is called a semiconductor. Examples, silicon and germanium. If the conductivity values lies below 10 power minus 7 Siemens per centimeter, the material is called an insulator. Example, glass, diamond, etc. Next, you are going to see the difference between metallic and ionic conduction. Till now, we have discussed only metallic conduction, that is, flow of electrons through metallic materials. Now, we are going to enter into the concept of electrolyte solutions. When you connect a battery across a metal like a copper plate, current will pass through the copper plate. How the current is passing through the copper plate? By the flow of electrons. Whereas, you take copper sulfate solution and connect a battery across it. Now also, current will pass through the solution. But in this case, the current is passing through the solution because of the ions present in the solution. In the case of metals, conductance is inversely proportional to temperature. Conductance decreases with temperature. At high temperature, conductance will be less. Because if you increase the temperature, we saw that the atoms are always vibrating in metals. The atoms will start vibrating more. You would have seen water boiling. If you increase the flame, the boiling will be more, just like that. If you increase the temperature, atoms will be vibrating vigorously. Because of that, resistance increases and conductance decreases at higher temperatures. Whereas in the case of ionic conduction, if we increase the temperature, ions will move faster. Because of that, conductance increases with temperature. This is an important difference between metallic and ionic conduction. Third point is, the composition of a metal does not change during conduction. Before and after connecting the battery to the copper plate, it is still the same copper plate. Its composition will not change. Whereas, you take a solution of copper sulfate and connect it to the battery, how current is passing through? By flow of ions. What happens when you connect a battery? Copper ions will move towards the negative electrode. That is, cations will move towards the negative electrode, and anions, in this case sulfate ions, will move towards the positive electrode. Because of that, before passing electricity, what happened? The ions were evenly distributed in the solution. After passing electricity, the ions are not evenly distributed. There are gradients. Near the positive electrode, more negative ions are accumulated. Near the negative electrode, more positive ions are accumulated. That is what we call as gradients. Final point is, the specific conductivity kappa is a constant for a given metal that we have seen just now. Whereas for a given solution, I said that for a copper plate, kappa is a constant. Can you say that for a copper sulfate solution, this is the kappa? The answer is no, because kappa of a solution changes with concentration of the solution, size of the cation and anion, and charge on the ions, whether it is a +1, +2, +3, -1, -2. So these aspects will change the specific conductivity value. So for an electrolyte solution, specific conductivity is no more a constant. How to measure the conductivity of electrolyte solutions? You can't just drop the battery in a solution to measure the conductivity. You need a specific setup called a conductivity cell. A conductivity cell looks like a glass tube. Inside the glass tube, there are two electrodes, two plates. Both are platinized platinum electrodes. You will see two black plates at the end of the conductivity cell. You have to immerse the conductivity cell in the test solution whose conductivity you want to know. Then you connect the conductivity cell to a conductivity meter. What is inside a conductivity meter? There is a Wheatstone bridge and a power source. Now what happens? You get the conductivity value for the solution. There is a specific constant for the conductivity cell called the cell constant, which is defined as L by A. L is the length, that is the distance between the two electrodes. A is the area of the electrode. Cell constant value is a constant for a given conductivity cell. For some cells, it will be 1. For some cells, 1.1. There are conductivity cells with 0.98 cell constant also. So we note down the cell constant value. Then when you connect it to the conductivity meter, it displays the resistance value. You get the conductivity kappa as cell constant divided by resistance. That is how you get the conductivity value, cell constant divided by resistance. Okay. One thing you have to notice here, in the case of a conductivity cell, both the electrodes are the same material. Whereas in the previous lecture on batteries and fuel cells, we used electrodes of different materials because we wanted to generate an EMF. In a Daniel cell, we connected a zinc electrode and copper electrode. We want to generate electricity there. But here, we just want to measure the conductance. We do not want any oxidation reduction reactions here. So when you dip a conductivity cell, you won't get an EMF. You won't see any oxidation or reduction reactions here because both the electrodes are same material, same dimension, same area, same dimension. So that difference you have to understand clearly. Next, we have seen that specific conductivity is not a constant. Kappa is not a constant for solutions. But we need some meaningful value, conductivity value for solutions, using which you can get additional information. So a new term called molar conductivity. It is not defined for metals. Molar conductivity, lambda m, is defined only for electrolyte solutions. We need a new term. Because, as I said, kappa is not a useful term for solutions because it varies with concentration. Second reason is we cannot distinguish between weak and strong electrolytes just based on the concept of specific conductivity. So molar conductivity term is needed for electrolyte solutions. What is the definition of molar conductivity? In simple way, it is conductivity per mole, okay, of the electrolyte dissolved in the solution. Conductivity per mole is molar conductivity. In textbooks, you see a detailed definition. It says conductivity of the volume of the solution containing 1 mole of the electrolyte. Quickly, you will learn why it is defined in this way. The formula for molar conductivity is specific conductivity multiplied by volume of the solution containing 1 mole of the electrolyte. Okay, why it is defined this way? If you take a 1 solution, 1 molar solution, 1 mole of the electrolyte will be present in how much volume? 1 liter volume. 1 molar solution means 1 mole in 1 liter. So here the V will be 1. If you take a 2 molar 2M solution, here 2 moles will be present in 1 liter. So that 1 mole will be present in half liter, 0.5 liters. For a 2 molar solution, what is the V value? 0.5. That is why it is defined this way. When you change the concentration, you have to take the V value, which contains 1 mole of the electrolyte. In simple way, you remember molar conductivity means conductivity per mole. Next, you have to understand very important and interesting facts about molar conductivity. If you understand these facts, the concept will be very clear. Okay. Just now we saw that molar conductivity is conductivity per mole of the electrolyte. So in thermodynamics, you have read many extensive variables like delta G, delta H, delta S, etc. They are also defined per mole. What is an extensive variable? It depends on the amount of the substance. It depends on the number of moles. Intensive variable means it is independent of the number of moles. Okay. Extensive variables depend on the number of moles. So we express delta G as per mole. 30 kilojoules per mole, 50 kilojoules per mole, like that. Here also we are saying molar conductivity is conductivity per mole. Now you should get the down. You have to combine concepts across different units to get clear idea. So you should get this question. So is it like any extensive variable that we study in thermodynamics? The answer is no. Because free energy delta G is an additive property. That is, when we say delta G per mole is 30 kilojoules, that is 30 kilojoules per mole, 1 mole. For 2 moles, what is the value? 60 kilojoules. For 3 moles, 90 kilojoules. So when you increase the number of moles, you can just multiply the number of moles by the per mole value. You get the final delta G value. But for molar conductivity, you cannot do like that. If I say molar conductivity per mole is say 140. For 2 moles, will it be 280? No. Because molar conductivity also varies with concentration. This will be shocking to you. Okay. Molar conductivity means conductivity per mole, but it is also varying with concentration. Now you should get another question. Why we introduce the concept of molar conductivity? Because specific conductivity changes with concentration. So we wanted a useful parameter. We came to molar conductivity. Now I am saying molar conductivity also changes with concentration. Then what is the use of molar conductivity? You can distinguish between strong and weak electrolytes based on the concept of molar conductivity. That is a very important use. Molar conductivity concept is also used to follow the reactions of coordination compounds. Based on the molar conductivity values, you can easily find out the stoichiometry of coordination compound reactions. Okay. Now, that is a very important purpose of molar conductivity. Now, let us understand why molar conductivity is changing with concentration of the solution and how it changes. Okay. General formula for conductance. You take any conductance, can be metallic conductance or ionic conductance, whatever conductance you take. The general formula is number of ions multiplied by mobility of ions. How many ions are present in the solution? That should be multiplied by how freely the ions can move. Okay. You can understand this by taking the example of food delivery. Okay. There are many online food delivery companies, you know. How fast the food will reach you, that depends on the number of delivery persons as well as how fast they can move. Through which route they are coming, you get a map, right? You can track. So through which route they are coming, through which vehicle they are coming, is there any traffic on the way? So in essence, their mobility. So number of delivery persons multiplied by the mobility of the persons will decide the speed of food delivery. Like that only, conductance is equal to number of ions multiplied by mobility of ions. This is true for both strong as well as weak electrolytes. For both strong and weak electrolytes, molar conductivity is inversely proportional to concentration. When you dilute the solution, molar conductivity increases. Okay. When you dilute the solution, molar conductivity increases. But the reasons and graphs are different for strong and weak electrolytes. That is how you can distinguish them. A strong electrolyte like sodium chloride is completely dissociated into ions. That is, if you take 100 moles of sodium chloride and dissolve it in water, you will get 100 moles of Na plus ions and 100 moles of Cl minus ions. That is what we mean by complete dissociation. When you dilute the solution, okay, what happens? The number of ions per mole is not going to change. Okay. Per mole, how many ions were present? Same number of ions will present now in a larger volume. That is the difference. The number of ions per mole will not change. On dilution, the same number of ions will be present in a larger volume. So what happens? Now look at the picture. You compare the same volume of a concentrated solution of a strong electrolyte with dilute solution of a strong electrolyte. Same volume. Okay. In a concentrated solution, in a given volume, so many ions are present. They are congested. Whereas in a dilute solution, in the same volume, less number of ions are present. As a result, okay, what happens? The ions can move freely in the case of dilute solution. Okay, the customers are the ions, like that you understand. There is a hotel, customers are coming. In the same space of the hotel, when more customers are there, the space is restricted, they cannot move, they have to wait. Whereas, in the same space, when less customers are there, they can move freely and sit anywhere. This is the difference. Customers are the ions. Okay. So when you compare the same volume of a concentrated solution and a dilute solution, a concentrated solution has more number of ions in a given volume, whereas a dilute solution has less number of ions. Because of this, ions can move freely in dilute solution, whereas in concentrated solution, the ions cannot move freely. So what happens when you dilute the solution of a strong electrolyte? The number of ions per mole remains same. Okay, per mole, number of ions will be same, whereas the mobility of the ions increases. Because of this reason, as the mobility increases, conductance increases when you dilute the solution. Okay, conductance increases when you dilute the solution. When you see how lambda m varies with concentration of a strong electrolyte, this is the expression. Lambda m is equal to lambda m naught minus a root c. When you plot lambda m versus root c, you get a graph, straight line graph like this. This is an equation of a straight line. When you extrapolate the straight line and take the y-intercept, the y-intercept is lambda m naught. Lambda m naught is called limiting molar conductivity at infinite dilution. It is almost zero concentration. It's not zero. That is infinite dilution. The unit of molar conductivity is Siemens centimeter square per mole. So in the case of a strong electrolyte, why lambda m increases when you dilute the solution because the mobility of ions increases. The number of ions per mole remains the same. This is the reason. Now let us look at the case of a weak electrolyte. Weak electrolyte, by definition, they are only partially dissociated. Example, acetic acid. You take 100 moles of acetic acid and dissolve it in a solvent. If the degree of dissociation is 40%, say. So, if you take 100 moles of acetic acid, only 40 moles of acetic acid will be dissociated into CH3COO minus and H plus ions. Remaining 60 moles will remain as CH3COOH. That is the meaning. That is the meaning of partial dissociation. When you dilute this weak electrolyte solution, now the dissociation is in the form of an equilibrium. So when I dilute this solution, the equilibrium shifts to the right. That is, more acetic acid molecules will dissociate. More number of molecules will dissociate. Now what happens when I dilute the solution? Number of ions per mole increases in the case of a weak electrolyte. We saw in the case of a strong electrolyte, number of ions per mole remains constant on dilution, whereas in the case of a weak electrolyte, number of ions per mole increases on dilution. As in the case of strong electrolyte, mobility also increases. When you dilute the solution, ions can move freely. So, in the case of a weak electrolyte, look at the formula. Both the number of ions per mole as well as mobility of ions, both the aspects will increase when you dilute the solution. Because of this reason, molar conductivity increases sharply with decrease in concentration of weak electrolyte. I hope you understood. So, molar conductivity increases on dilution, both for strong and weak electrolytes. In the case of strong electrolytes, molar conductivity increases slowly on dilution, whereas in the case of weak electrolytes, molar conductivity increases sharply on dilution. Whereas specific conductivity, it always decreases on dilution. Okay, specific conductivity will always decrease. Final topic is Kohlrausch law of independent migration of ions. It is based on the lambda m naught value. See the word independent migration of ions. When you keep on diluting a solution, whether it is strong electrolyte or weak electrolyte, you keep on diluting, keep on adding the solvent. Now what happens? It goes to the stage called infinite dilution. You know, in concentrated solution, the positive ions and negative ions, you take sodium chloride, Na plus and Cl minus ions, they always move in pairs. We say ion pairs because there is always an attraction between positive and negative. So in a concentrated solution, Na plus and Cl minus ions, they will always move together. Although dissociation is complete, but they prefer to move together. When you dilute the solution, when you go to the stage of infinite dilution, now there is more solvent and very less amount of salt. Now the positive and negative ions, they don't come close to each other. You know, electrostatic force is a short range force. It will operate only when the ions are nearby within a particular distance. Now the ions have moved far away, so they can move independently. That is why this law is called the independent migration of ions. So here the key word is this law is applicable only at infinite dilution. The law states that at infinite dilution, cations and anions move independently in an electrolyte solution. This law is applicable to both strong as well as weak electrolytes for both the cases. So you can write a general expression for any electrolyte MaXB, lambda m naught. This is not for lambda m. This is for the limiting conductivity. Lambda m naught is equal to A lambda m naught of cation plus B lambda m naught of the anion. This is the concept of Coleridge law. So today we have discussed the concepts of resistance and conductance, how to classify materials based on conductivity, what is the difference between metallic and ionic conduction, how to measure the conductivity of electrolyte solutions using a conductivity cell and Wheatstone bridge, and what is the concept of molar conductivity, how it varies with concentration, how you can distinguish between strong and weak electrolytes based on the concept of molar conductivity. And finally, we have discussed Coleridge law of independent migration of ions. Dear students, I hope you understood and enjoyed this class. You can expect more and more topics to come in the near future. If you would like to get more materials for NEET, you can browse the Amazon Kindle store. I have given the links in the description box. You can see topic-wise simple notes with solved problems from 25 years of NEET papers, as well as you get a free quiz and access to free video lectures. If you are interested in attending online chemistry classes at your convenient time for NEET and Class 12 chemistry, you can put an email to nflacademy@gmail.com. All the best, students. Enjoy chemistry.